Hi, I'm Menkit. Now I'm going to do an introduction for our presentation. So, program synthesis or code generation is being used to generate programs that can fulfill the problem specification. Recent studies are using the technique of pre-trained language model, yet is having some limitation. So our presentation is about a new framework for program synthesis tasks called RL using pre-trained language model and deep reinforcement learning. As you can see at the right figure, a pre-trained language model receives an input sequence as problem specification, and it generates an output program of code. But for some complex problem, the model will fail to generate the code. At the left figure, it is an overview for the code RL. The pre-trained language model is the policy. The code generation is the action, and the rewards are from the unit test result or output program. Then my teammate will continue.
Thank you, Minghin. Hi, my name is Lee Xintian. Let me now move forward with the related work. Program synthesis, the process of automatically generating programs from high-level specification, has been a central topic in this research. It can be traced back to the early days of machine learning research, with early tasks focusing on input-output examples, probabilistic approaches, and simple programming concepts. With the rise of deep learning, later methods leveraged neural networks to generate output programs. These models benefited from inductive biases introduced by large dataset of program samples, enabling the generation of increasingly complex programs from high-level specifications. More recently, program synthesis has expanded beyond basic programming tasks to address more complex challenges, including the use of general-purpose programming languages. Modern approaches aim to generate full programs for natural language description written in English. It also leads to the increased use of pre-trained language models, as those models leverage vast amounts of contextual knowledge from training on diverse text data. Despite these advances, existing models still struggle with more complex programming tasks. Another important area of program synthesis research involves the visual domain, including images and videos. Early work in this area introduced inverse graphics networks to infer properties of visual objects. As the field progressed, research extended to image rendering, where methods focus on transferring raw images into structured and compact representation, providing a foundation for applications such as image editing, captioning, and extrapolation. However, this body of work is largely limited to domain-specific languages. In contrast, this work focuses on program synthesis from natural language problem specification, where the output is expressed in general-purpose programming languages such as Python. This shift enables a broader range of applications, from basic coding tasks to more complex problems. A significant body of work has explored the use of reinforcement learning (RL) to optimize sequence generation tasks. Early studies adopted the reinforced algorithm to directly optimize models for sequence-based metrics such as BLEU and Roach, which are commonly used to evaluate the quality of generated text. Building on this, actor-created frameworks were introduced to further improve translation models by enabling them to make better decisions during training. In the image captioning domain, RL has also been applied to optimize models that generate textual description of images. Research has explored the use of visual semantic embeddings to derive goal-oriented return estimates, improving the performance of captioning models. However, when applied to program synthesis, traditional token-based similarity metrics like BLEU have been found to have poor correlation with the functional correctness of generated programs. In response to this challenge, this work introduced the CodeRL framework, which optimizes program synthesis by incorporating unit text signal to verify whether a program works as intended. This CodeRL is related to prior work on R-based program synthesis and execution-guided synthesis approaches, but those were limited to programming languages defined within specific application domains. That concludes my part. Now I will turn the presentation over to Wei Heng.
Thank you, Xintian. So let's continue on with the method that the author proposed. Firstly, the author defines the objective function, also known as the loss function of the model. In this model, they use a cross-entropy loss as the loss function, which is calculated as the sum of log of probability of the output W where the input sequence D is given. Further elaboration of the function, it can be written as given D and output W from the previous time step, what is the probability of the output W in the current time step. Here, the predicted output W is calculated by the hidden variable across the linear layer following with a softmax activation function. This is the architecture of the model proposed by the author. In this figure, we can note that the model is trained firstly on the public code on GitHub. Then it is fine-tuned with QA dataset formed by the problem and solution pair supervised. After fine-tuning, the model will be further optimized using an actor-critic network, where the actor network will generate a solution based on the problem given, while the critic network will give the feedback for the solution. This is the base language model used in the article where all the methods will be implemented based on this. The base model chosen is code T5 trained with the code generation data set using the T5 model by Google. Here is the loss function in the actor critic network, where we can view the delta as the policy learned in the fine-tuning process just now with the base language model. It will be responsible in deciding the action chosen for the next step. Here we can see the loss function is defined by the author as the negative of the expected returns from the network. This means that it aims to minimize the return, also can be understood as minimizing a loss. For example, when the expected return is negative 100, the network is always given a bad solution. From here, we can get the loss as 100, which is quite high in this scenario. This is the reward set by the author. We can see that only when the solution program from the language model is working properly, it will receive a reward of 1. In other cases, it will receive a reward of negative zero point 0.3 to negative 1. To get the model to train better, the author adopts a baseline model to guide the code RL model from the loss function. We can see that the loss will be calculated from the difference of the baseline model and code RL itself. So here is the overview of the actor critic part. We can see from here, the model will be given a problem initially to generate a solution. Then the solution will be tested with some unit tests. If it passes, the solution will be used to sample subsequence with the critic model, where it will become a seed to regenerate problems for the language model. PS. All the generated solutions will be stored in a replay buffer for further usage, even the failed ones. Finally, the author defines the loss function for the critic model, which is given problem D and solution W. What is the probability of unit test U? U is the unit test given by the critic network to examine the quality of the solution generated by the actor model. So that's all for me. I will pass it on to Chari to talk about the experimental detail part. Thank you.
Thank you, Weihen, for your presentation. Now I'll move to introduce how they test their model's performance. Before the experiment, they design the workflow in 4 key steps. The first one is about their model with size of 770 million parameters. Then test the model based on APPS benchmark datasets with fine-tuning setup. Finally, they get the evaluation of the model's performance. This slide shows the model's performance based on APPS benchmark dataset. From both of the tables, we can find that the code RL and T5 model can perform better than all of the models above in most of the situations like GPT-2 and 3, even with much smaller model size. This means the model performs quite well. To better understanding the contributing factors to the model's performance, they did ablation studies. The first one is about return estimates. For the table showing They want to figure out in which estimates case the model can perform better. Obviously, in case D, with return estimates existing, the model can get best performance. The second one is about different learning objectives. From the table, we can know that in same situation of learning objectives, the two models can perform quite different. But generally, T5 can still perform better than GPT-Neo based on the shown values. The third one is about critic sampling. Normally, in each case, the model with critical sampling can perform better than the one without critical sampling. And then is about variants of pre-trained models with a different size, tasks, and data. The table shows that when the model equipped with size of 770 million parameters plus GCPT data and NTP task, it can get best performance than any other cans. Finally, it's about the results based on MDPP dataset. With the rule that the higher score, the better performance, we can conclude the code RL and T5 model is still performing better than GPT even with different version of the size. Generally speaking, the code RL and T5 model is trained with excellent result compared with different large models. That's all my part, and now I'll pass it to Minhing. Thank you very much.
Then, I will explain the limitation of this work. The one limitation of code RL is the computation cost for training critic models to estimate returns in addition to the original language model. Another limitation is that the risk of it. For example, training data from public codes may contain vulnerabilities, and the resulting model may generate programs with weak security measures. Finally, I will have a conclusion. Code RL use deep reinforcement learning techniques to improve the performance of pre-trained language model by exploiting unit test signal in both training and inference steps. An actor-critic training approach is used to optimize pre-trained language model, and critical sampling is used to automate program generation. The integration of Code RL is performed by using Code T5 large model, and it is achieving better results than common pre-trained language model. To end with, Code RL is a general framework that integrates pre-trained language model and reinforcement learning holistically for program synthesis, and it has the potential to be improved. For example, it can be easily integrated with better trained language models and can be improved with more fine-grained feedback from the environment. This is all for our presentation. Thank you.